Alright guys, we are done with physical science for the year. The stuff that we are talking about still has a little bit of the physical science content, but it will not nearly be as intense as the math and stuff that has been involved in the past few chapters. We are moving on to some earth science stuff, and we are going to start earth science with plate tectonics, internal processes, so earthquakes and volcanoes, the layers and structure of the earth. So our first section has to do with the evolution of the Earth's crust and how we got our continents and oceans and stuff where they're at right now. Kind of think of this as a little bit of a story, and our story really starts in the early 20th century when people started to think about the Earth and how things are moving and acting and behaving the way that they are. Why are these volcanoes erupting? Why do we have these earthquakes? There was no theory about how all of these things were connected. So in 1915, a scientist named Alfred Wegener proposed a hypothesis. Okay, it's a hypothesis, so an educated guess that all the continents were once connected together, part of this larger supercontinent called Pangaea. Okay. As he was talking to other people about his hypothesis, it was not accepted by the scientific community. And it wasn't accepted because he could not explain how, if they were once part of this big, massive supercontinent, why do we now have these different continents all spread throughout our world? He didn't know how they got from point A, this large supercontinent, to where they are now. So, like any good scientist, he had to start looking for some evidence. So he used the coastlines of the continents. He did not use continental shelves. Coastlines, as time goes on and the ocean waves beat up against them, they erode away. So the coastlines do not match up perfectly, but he thought if I push these all back together, I can kind of see how the eastern coast of South America would match up roughly with the western coast of Africa, and I can see how North America's eastern coast could kind of get pushed in together into that Europe and Africa western coast as well. Later on, once we get sonar, we'll talk about continental shelves and what we found there. But know that Wegener used coastlines. Okay, he used some fossil evidence. But when you look at fossils, you've got to be careful which fossils he was choosing for backing up his hypothesis. He could not use birds. He could not use plants that have seeds that could be airborne for a long period of time. So he had to use large land-dwelling mammals that would not be able to cross an ocean. And he would have to use plants that had very large seeds, such as ferns, that would drop pretty much instantly, that would not be able to carry through the air. He also looked at matching rock layers. As he looked at some of the rock layers on Africa and Europe and matched them to the American rock layers, they matched, and rocks form based on the conditions of the environment at the time when that magma erupts from the volcano. Okay, whether it's quick cooling conditions or slow cooling conditions, depending on what minerals are in that magma, are all going to determine what rocks are formed. And they're going to be very minute differences, but when he looked, these rock layers matched up lovely. Okay. However, he still could not say how do these continents move. So we finally get an American named Harry Hess that used sonar to start mapping the ocean seafloor. Sonar uses sound waves, so he was able to drop the sonar into the ocean, and sound waves would bounce off the bottom of the ocean floor and bounce up, and he could start mapping it. This is after World War II. This was a technology that was used during the war to help find submarines. Okay. As he was mapping the ocean floor, he found a feature called the mid-ocean ridge. This we will also refer to as MOR. If you look here on this image, the MOR is that very dark area, okay, that is right in the middle of the continents. Okay, and he didn't know exactly what this MOR was, but he found it very interesting that there was this mountain range there, and that something had to be going on because it was seemingly in the exact same physical shape as some of the continents. If you look at how that mid-ocean ridge is shaped, you can very easily see how it would be adjusted. The other thing that sonar helped us determine is these continental shelves. As we look again at this picture, okay, there are areas surrounding the coastlines before the continents really drop off. Okay, these areas are underneath the surface of the water, so they are not subject to the erosion. And if we start to look at these continental shelves, the continents match up perfectly. Okay. As we started to do more research on the mid-ocean ridge, we found that the oldest rocks are found near the continents, and the youngest rocks are found near the mid-ocean ridge. That got him thinking, how is this working? Why are these old rocks right near the continents? How are these young rocks right by that mid-ocean ridge? Well, we know that the mid-ocean ridge now is made up of volcanoes, and as those volcanoes erupt and the lava cools, they form new rocks. So as the new rocks are cooling, they have to push the old rocks aside. Okay? Think of it like a conveyor belt that you have at the supermarket. So this all kind of came together and supports Hess's theory called seafloor spreading, that at this mid-ocean ridge, the continents are spreading apart and pushing the old rocks towards the continents. As we continued to look at the seafloor more and learn more about it, we learned that the rocks of the seafloor, which is basalt, is a high iron content. And iron is a magnetic property, has magnetic properties, which record the polarity of the poles at the time. So if we start looking at the seafloor, you can see when the North Pole was where it is today, the magnetic North Pole, and where the magnetic South Pole is today. There are also times when these poles have been reversed. Okay, so the seafloor basically starts acting like a compass and gives us these north and south poles like they are now, and gives us north and south poles being reversed. And if you kind of look at the seafloor in this magnetic sense, you start to get stripes on the seafloor. Okay, let me start off by saying the seafloor is not actually colored like this. These stripes are here to help you recognize the normal fields, okay, where north and south is just like it is today. Those are the red segments, and the reversed fields. So you can start to see this geological history being shaped on the ocean seafloor. This theory of seafloor spreading, along with using Wegener's theory of continental drift, all kind of brought together in the 1960s and led to the theory of plate tectonics. Okay, it's a theory, so remember this is an explanation why. It's not telling us what happens, it's telling us why things happen. Okay, this theory states that the Earth's surface is made up of separate slabs called plates. These plates move slowly over the Earth's surface over time. By slowly, we are talking 1 to about 4 centimeters a year. It is not going to be a rapid pace that these plates are moving. It's much like your fingernails. They're not going to shift overnight, seemingly. When we do have earthquakes, they do shift overnight, but they are moving slowly over time. As these plates are moving, they interact with each other where the plates are connected. We call those plate boundaries. Okay, and then different things happen at those plate boundaries depending on how the plates are interacting with each other. Right, so 3 types of plate boundaries that we have: divergent, convergent, and transform. And each one of these behaves, and the coastlines, or where the plates interact, those plate boundaries, look very different. So let's first look at divergent plate boundaries. These are where plates move away from each other. When plates move away from each other, you would think that you would get this big gully where there's nothing there. But we can't have that. So what happens is magma rises up between the plates, spread out, cools, and becomes new crust. So at divergent plate boundaries, we are getting new crust. We talked just a few minutes ago about a land feature that Harry Hess found called the Mid-Ocean Ridge. The Mid-Ocean Ridge is a divergent plate boundary. Another plate boundary, or divergent plate boundary, is in rift valleys. And one of the most famous rift valleys is the East African Rift Zone. And this is an area in East Africa where the plate boundaries are moving apart. So if you look here, you've got some plate boundaries right in here. Okay? And seemingly, you've got plates moving this way and plates moving this way in here. And all of this is kind of spreading out. You can see all these little triangles. Those are volcanoes where this area is spreading apart and new continental crust is being created. Convergent plate boundaries. These are where plates come together and collide. There are 3 different types of convergent plate boundaries, and what happens at each convergent plate boundary really depends on the density of the plates. Just like we had density differences when we talked about thermal expansion and heat, okay, less dense stuff rises, more dense stuff subducts, okay, or forced downwards. So when we look at the convergent plate boundaries, whatever is less dense is going to rise up. Whatever is more dense is going to be forced downward in a process we call subduction. The three types of convergent plate boundaries are continent-continent, continent-ocean, and ocean-ocean. We're going to take a look at these three types in more detail. First one is continent-continent. So we have two continental plates of equal density colliding. Since they are equal density, neither is going to rise, neither is going to subduct, so they're going to buckle together. And when these two continental plates buckle together, we are going to have a mountain range being formed. An example here for you is the Himalayan mountain range in Asia. Okay, a very active plate boundary. I think you probably remember from a few years ago when there was the earthquakes in the Himalayan mountains in Tibet. That is because the Indian plate is moving towards the northeast and the Eurasian plate is moving towards the southwest. And they are both continental plates colliding with each other, so you get this mountain range being forming. So the Himalayan mountain range is actually still growing because these two plates are still colliding in with each other. Second type of plate boundary is called continent-ocean. And here, the oceanic crust is more dense, so it is forced downward. It subducts underneath the less dense continental crust. As that oceanic crust is forced downward in the subduction zone, okay, heat starts to take over and melts the rock. And that melted rock then sneaks through cracks in the ocean and forms volcanoes. An example here is off the western coast of South America, where you get the Andes mountain range. So looking at the picture here, you have your more dense oceanic plate, shown here, subducting under the less dense continental plate. As the rock from the ocean crust subducts, it starts to melt and is forced upward through cracks in the Earth's crust, and you get that volcanic mountain range. So if you see volcanic mountain ranges near a coastline, you can reasonably assume that there is a continental oceanic plate boundary going on there where the ocean plate and the continental plate are colliding together. Final type of convergent plate boundary is ocean-ocean. Now here you would seemingly assume that because we have two of the same plates, we're going to get more mountain ranges. However, ocean crust is different because the temperature of the ocean is very variant throughout the ocean seafloor. So colder crust is going to be more dense and it is going to subduct under warmer, less dense ocean floor. Again, colder, more dense subducts under warmer, less dense crust. Here you get magma then erupting because you get those subduction zones again, just like the last subduction zone, but now we're dealing with ocean and ocean continents, or ocean-ocean plate boundaries. An example here, you get volcanic island chains. Now you have to be careful because as soon as I say volcanic islands, you're going to think Hawaii. Hawaii is formed in a completely different matter, which we will talk about later in this chapter. But an example here for you is the island of Japan, okay, or the islands of Japan. You get this boundary here because you've got an oceanic crust going this way and an oceanic crust going this way. And one subducts under the other and sneaks through the cracks as that crust melts, and you get active volcanoes again. Okay. Last type of plate boundary is called transform plate boundaries. Here you get a horizontal sliding past each other. Your example here would be the San Andreas fault line that I think that you guys are fairly familiar with going through California. Okay. They can be in transform plate boundaries, sliding in opposite directions, or they can actually be moving in the same direction, however, moving at different rates. So your mid-ocean ridge is also an example of some transform plate boundaries. You've got these different plates all moving in the same direction, but moving at different rates. So you get some sliding going past each other there as well. So 3 different types of plate boundaries, but we still haven't answered the question of what moves the plates. What causes these plates to interact with each other? Well, it's really caused by a combination of different forces. First is ridge push. Here where we get ridges, okay, the mid-ocean ridge, okay, those rift valleys, the divergent boundaries, okay, push material down the slope. Okay, as I add something to the back of the conveyor belt and the conveyor belt's full, if I want to keep adding, I have to push things off the other edge. So that's our ridge push. Next is slab pull. This happens at convergent plate boundaries. Okay, think of this as something sliding off the side of a lab bench. Okay, as it starts to go, okay, it moves seemingly slow, but as more and more starts to hang off the edge of the lab bench, eventually it's just going to fall straight off. Another example is tossing and turning in your bed at night, and the covers slowly make their way to the end of the bed, and gravity helps pull them down off your bed then. Finally, you get frictional forces. Frictional forces happen between the layers of the earth. And as one layer of the earth moves, another layer of the earth moves. So they kind of drag each other along because of that friction. Okay, if I have a couple of things stacked on top of each other and I move the bottom layer, the top layers are going to move along as well. Scientists also believe that there are roots of the continental crust deep inside the earth into the mantle layer. Okay, much like a tree has roots into the soil. And finally, we have thermal energy playing a part in all of this. Thermal energy, okay, deep inside the Earth's core, there is a large amount of heat. That large amount of heat needs to escape, going from where it's hot to where it's cool. And you actually get convection cells going on within the mantle. And those convection cells are really driving both the ridge push and the slab pull, and are the reason why we have these frictional forces moving things along as well. So let's take a look at this picture and see what's going on. So you've got your heat, okay, here within the inner core that wants to escape out. Okay, it wants to go where it is colder. So out here it's cold. Okay, as it continues to come up, some of that makes it through and becomes new crust. As it becomes new crust, it pushes the old crust off to the side. Okay, there's your ridge push. Eventually, we get two plates colliding together in a convergent plate boundary. Okay, convergent plate boundary. And things start to subduct. Okay, and here, as this slab starts to go underneath the other continental crust, it starts to pull the crust with it. Okay. Here you can easily see the convection cell, okay, and then you get your frictional forces right along these plate boundaries, or the Earth's boundaries of the different layers of the Earth. Okay. Lots going on here, lots of terms. I highly suggest you make some flashcards so that you can remember all the differences in plate boundaries. You can remember the people. You do not have to know time of dates, so you don't need to know when Alfred Wegener proposed his theory. You don't have to know when sonar was used by Harry Hess. You don't need to know when the theory of plate tectonics was put together, but you do need to know who was associated with those items. When you're done listening to this, make sure you are set and ready to go for lab on Thursday. We will be using the probeware, and we'll be doing something similar to what Harry Hess used in mapping some seafloor. Have a great day. Let me know if you guys have any questions. Bye.